Good morning, ma'am. Good morning, everyone. Again, welcome to the third day of our SINSM Track D. I hope everyone is still safe today. And before I introduce our last speaker, I would like to just share with you the web netiquettes. Please bear with me. Okay. For all attendees, please observe the following etiquettes. Turn off your microphone and webcam during the talk. Please post all your questions in the chat. This will be asked by the moderators at the end of each talk. Towards the end of the last presenter scheduled for the day, the link for the evaluation form will be posted. Again, certificates will be awarded to attendees who attended at least 75% of all the talks in the workshop. All right. Our last lecturer is our professor. He is a professor at the University of the Philippines, Baguio. He finished his BS Math in Mathematics in UP Baguio and completed his Master's in Applied Mathematics and Computer Science and PhD in the University of the Philippines, Diliman. He, part of his interests are epidemic modeling, mathematical modeling and simulations, numerical computing, and evolutionary optimizations. He is a member of PAASE, SIAM, IEEE, ACM, MSP, and CSP. Here to give his talk on the introduction to agent-based modeling of disease dynamics, let us welcome Professor Joel M. Adawe. Over to you, sir.
Thank you. Can you now hear me? Hello?
Yes, sir.
Okay, let me share. Can I share?
Yes, sir. Please go ahead.
Am I allowed to share?
Yes, sir. Yes, sir.
Okay, so let me share my presentation for today's lecture. I've given this lecture initially, and I hope for those who have attended and listened, then some topics will be repeated. Okay, so again, can you now see my screen? It's a white screen.
Yes, sir.
Okay, so again, I'll be giving a talk this morning, and in the afternoon, we continue and try to demonstrate on how to make use of some existing agent-based modeling. Okay, so before we play around with that kind of package, then we might as well have an idea first on how to model diseases. Okay, so I hope most of you here are familiar with at least a knowledge in calculus. Okay, so let me check first who are the participants. I think most of you are graduate students. Am I right? So, Ma'am Cindy, lahat ba? Anyway, yeah, I think most of you are in the graduate school, okay, or maybe are at least familiar with differential equations, okay? So for those who are familiar with this section, then I hope you bear with the others who will be new or who are new to this topic. Okay. Okay. So what happened? Uh, can you now see? Right? Am I having
Yes, sir.
problem with this? I get distracted on all the one logging in and keeps reminding me to admit. Okay, so the outline of the talk, title will be disease modeling using agent-based approach. Okay, and as I've mentioned, we will give you an idea on how uh, diseases should be modeled in such a way that we will be able to incorporate them in an agent-based modeling software. Okay, and look at the differences, why we make use of agent-based and some other tools, okay, to simulate disease models. Okay, so the outline of this talk would try to cover the following: an introduction, a little background on how uh, or a little history of diseases, okay, and again, we'll look at simple models and how these models uh, should be represented, and try to formulate the mathematical model. And from there, we either do uh, analytical analysis or some simulations to visualize what is happening in the dynamics of the model. Okay, so I will concentrate on agent-based modeling using Gamma, which for me is also a new one. Learning the package is quite steep because again, you will not be able to what do you call this, understand the model unless, or rather the examples, unless we have an idea on the basis how the model are constructed. Okay, so take note that when we do simulations, it is important to know the equations governing the model, because again, the equations will be the things that we need to input in our model. Okay, so it's not just writing the code wherein you just make use of loops, but rather understand how this equation should be constructed. Okay, so that we'll be able to see the limitations and construct also the algorithm. Okay, so agent-based modeling will use Gamma, and then how a little comparison of a deterministic approach and an agent-based approach. Okay, so we know that again, diseases are very important because currently we have a pandemic, and it is really nice to look at how we can make use of tools to study the dynamics of the disease. Okay, so in some of the things that happened before, okay, as we can see, uh, diseases really or can also be seen as early as BC, 700 BC. Okay, so we can look at certain decisions that were made, okay, and the things being done by modelers to help decision makers. And as you can see in the news uh, today, especially the way how they tackle COVID-19, we now have people working in the medicine and at the same time in the sciences, okay, who are modelers like we have medical people, statisticians, engineers, computer science, and mathematicians and physicists. Okay, so again, just like before, there are certain people that were top, okay, for them to help uh, on how they decide, okay, on certain things. Currently, you have different groups tackling COVID, okay, and these groups are an interdisciplinary group wherein, again, input from different fields are being considered. Okay? And just to go back to some years where the first known result of mathematical epidemiology was uh, done when Bernoulli did analysis for smallpox. So you can see that as early as 1700, there was already a study on the use of mathematics, okay, to analyze a particular disease. Okay. And what is nice also is when we look at the concept of compartmental modeling, where this is the section that I will be dealing with. Okay, so when you deal with epidemiological modeling, there are several aspect or tracks that you can look into. Okay, so in this case, I will just look at the compartmental approach, where it was started by Rosen, McKendrick, and Kermack. Okay, and as early as 1900, they started working on these simple models, and this is the basis of our discussion, and it's really nice to really look into the basis of the more complex models that we are dealing with now. Hey, again, what's the goal of using mathematical models? Uh, it's a cheaper way of trying to solve certain problems, because again, we cannot sometimes solve realistic problems just by doing experiments, but rather trying to translate it in such a way that will not deal uh, with humans, okay, particularly, but rather some sort of a representation of uh, the humans that we want to deal with. And uh, you now have several papers and articles which are working on different diseases. Okay? And again, when you look at a particular disease, you get to contract the disease either by the same person that has the disease or by a vector. Okay? Meaning there's an intermediate uh, uh, step where the disease will be transmitted. Okay? And due to the information that we need to process, then we really have to make use of computers, okay, to process very large information. And as we can see in the different universities abroad, you have also different groups who are trying to solve the current pandemic, which is COVID-19. Okay? So at present, I think we have the group here in the Philippines. We have several groups. The OCTA group, which is led by uh, some professors in UP Diliman. Uh, Fortunately, their math modeler is also from the Institute of Math. Okay, so that's why you always see or hear the name of Guido, okay, which is also my co-author in one of the papers that we've worked with. Okay, again, we might as well ask questions when we deal with models. We really have to look at several questions. Okay, so why do we model, and what are the aspects when you deal with the model? Okay, or what are the parameters and variables that you have to deal with when you model? Okay, and then what are the different mathematical modeling methodologies? So there are several approaches that I have, as I have mentioned, but in this case, we'll just be dealing with the compartmental approach. Okay, again, I'll go back to the usual process that I always look into, where if I sit down and try to solve a problem, okay, or maybe you have observed some problems, what you usually do is either you try to solve it, or in my case, what I usually do is apply what I am familiar working with. So it's in the math world, meaning if I have to look at a real world problem, then what we can do is do a solution, meaning directly, and that can be done. The direct path here would be looking at a direct solution, okay, or doing experiments. Okay, but in this case, what we can do now is try to look at the real world problem and translate it to the mathematical world. So I'm looking at the lower rectangular box here, where given certain problems, instead of going directly to solve, uh, come up with a solution to the real world, what we can do is put it in the lower region or in the lower rectangles here. And what we can do is come up with a math model. Okay. So in the math model, uh, we have to make assumptions, and then we also have to make some representations of the real world problem. Okay. Once you are in the math world, then what we can do is to make use of the rules that we are familiar with, okay, and come up with a particular, rather a solution to that math model. Okay. And here, what we can do is you solve. So given those variables and parameters that you have incorporated, and certain governing rules or equations that you have derived, okay, or as a way of representing the real world, then we try to solve the math model. Okay, so in solving, you have different tools that you can uh, make use of, okay? And most of you would be familiar with. Once you have a solution, then what you can do now is translate it back to the real world. Okay, meaning the solution makes sense. So if it doesn't make sense, then what we can do is make some revisions, tweaking, and again it goes to the real world problem and then translate it back again to the math model. So what happens here is some sort of a circular process, where first come up with the mathematical model, and then try to solve, and then translate or interpret. Okay, and so we can see it's not always the uh, correct solution, or not close to the solution, but at least we have an idea of a possible solution to the real world problem. Okay, so here that's the usual mathematical modeling approach. And next is some modeling methodologies. In particular, we'll deal with disease dynamics. So we will try to model a particular disease, and uh, you have different ways of doing and solving the problem. Okay, so we can have a statistical based, mathematical space models, or machine learning based models. Okay, so here you will see that there's some intersection, meaning it's really nice to really incorporate all the three uh, branches here, because again, as we can see, there are certain advantages and disadvantages. Okay, so what is really good here is to integrate and combine the different approaches. Okay, so here in the mathematical space models, what we can uh, consider is using a analytical approach or a numerical approach, in which case, uh, since I think you have taken track D where you had Java, then it's nice that Java is also a tool that is being used in Gamma. Okay, but again, the usual or any programming language that you're familiar with is helpful in learning how to make use of Gamma. Okay, now, so if I were to look at the disease dynamics, then there are certain models that are already present, like the concept of Hermack and McKendrick, where the simple models of the SIR, okay, was based. And as you can see, this is how it started, where a simple model like a SI or SIR, meaning when I say SI, you try to look at, since you're dealing with the disease, especially in humans, so it can also be possible diseases in animals, but in particular, you have a particular species wherein you try to uh, divide the human population or a particular species. Like if you're dealing with animals, then you divide the animal population into compartments. Okay, meaning you can either divide it into two, where if I were just to deal with humans, then the two compartments that I can consider is the population of susceptible humans, meaning uh, humans that can acquire the disease, and the other compartment is the infected humans. Okay? So in that case, you will have an SI model, and once we have the model, then what we do is come up with a, so what is now happening is you try to translate it to the math world and then construct a diagram so that you can have a visual approach of uh, the problem, at the same time being able to come up with the governing rules or equations to uh, define the problem. Okay, so in that diagram, you can construct diagram, because diagrams again is a way of visualizing things. Okay, and once you construct the diagram, then you can have the model, the mathematical model, and this can be governed by equations, linear or nonlinear. And once you have that model, then we can try to solve it directly. Okay? Solving directly means you either use an analytical approach or a numerical approach. Okay? And from those solution, so you are dealing with a mathematical approach, then you can come up with a solution. Okay, so what we're trying to do now is try to look at the dynamics as it moves through time. Okay, the other approach is using face portraits, meaning since it's not sometimes or it's sometimes difficult to solve analytically, then what we can do is just try to study the dynamics where you can make use of face portraits. Okay, and in this process, what you can now do is to solve uh, some equilibrium points of your system, and then do stability or sensitivity, and also uh, look at other things. Okay, and another simple model would be SIR. The usual thing that you can do is the same thing. You construct a diagram, okay, and then once you construct a diagram, then you formulate a model. Under the model, it goes to the uh, branch of solving directly, or using or studying the dynamics using uh, face portraits. Okay, and another variation would be once you have an idea of an SI model, then maybe a particular disease would incorporate vaccination. So in that case, it again divides the compartments where you can consider uh, SIR uh, with vaccination means that you have a different compartment where you have people which are being vaccinated and the other which is not vaccinated. Okay, so the diagram will also be of help again. So how do you construct it? Either you have a separate uh, compartment for vaccination, okay, or it's possible that vaccination will just be a direct path from the susceptible population to the recovered population. So it's just like a shortcut. Instead of going to the infected class, then you just have an arrow which goes from what do you call this, from the susceptible directly to recovered. Okay, so that's another way of interpreting it. And other models like with the exposed class, so you can have an SEIR. So you have four compartments, or other compartments that you can incorporate would be again dividing the humans into subpopulations. And once you come up with more compartments, then it makes the what do you call this, the problem more complicated because it will involve more equations governing the compartments. Okay. So other models, as you can see, models that they're being considered in modeling COVID is again as simple as SIR or SEIR. Okay, but doesn't mean that it's as simple as SIR, because the parameters involved in the movement of a susceptible class to an infected class can be defined in terms of what we call the rate of infection. But the rate of infection is dependent on different parameters. So you can now integrate several parameters in the rate of infection. Okay, so you either have it is dependent on how a human person will be moving, okay, or a particular person current health. So if you have if you have people with comorbidities, then it's a different value for the transmission rate. Okay, so you can consider all those uh, factors, which makes the simple diagram SIR to contain more parameters. Okay, so that's how we uh, look at it. That's you have now an idea wherein just learning the simple SIR model would be a what do you call this, a basis to come up and solve your own model, okay, for a particular disease. Okay, to perform compartmental modeling, again, we need to argue on certain assumptions, meaning it's like when we play a game, we first agree on the rules of the game, okay? So that once we play, then we are able to follow and do what should be done, and at the same time understand what we're trying to do. It's the same thing in modeling, wherein in order for you to uh, have equations that will govern the particular problem or the model, then we should lay down the governing rules or the rules of the game. Okay? So in this approach, we are looking at a population, again, divided into compartments. In this case, let's look at the human population. So let's consider, let's say, as simple as colds. Okay, uh, we have humans which does not have colds, and some who have currently infected with colds. Okay? So we can now try to divide the compartments where we have susceptible and infected. So diseases that confer immunity have different compartments, which means that we can have a, uh, a region where if you have acquired the disease and you have recovered, then you can look at a compartment where you have the recovered population. Okay. Now, if you are to look at an SIR model, meaning one direction, we go from susceptible, it goes to infected, and you go to recovered. Okay, so once you recover, then it's possible that you don't get the disease anymore, which means you just stop at the recovered compartment. You don't go back or move back to susceptible. Okay? But as we can see, I think if I have recovered, then it's possible that certain mutation occurred in my body. Thus, if I recover from that particular disease, then it's possible that my body was able to uh, create some mutation of the virus that was initially initially I have acquired. Then it is now a possible way of interpreting a movement from the recovered class to the susceptible class. So it means that you are now looking at a possible scenario where you have recovered and you have temporary immunity on that particular disease, okay, and possibly go back again to susceptible. So you now have a movement of people from the recovered class to or back to the susceptible class. So you can now interpret that kind of model wherein you have a mutation of the disease, or simply a what you call this, a disease wherein once you acquire the disease, you recover, but at some point take some time before you are able to acquire the disease again, which means that after some time, then you have when immunity then go back to the susceptible. So that's one way again to interpret it. So you're looking at how you would transfer people from one compartment to the other. So uh, if I were to move from susceptible class to infected class, then I am able to look at the transfer of humans from the susceptible to infected. Okay, that can occur when I have the interaction of susceptible and infected. Okay? So if I get to transmit the disease directly to a particular infected person, then that's a direct transmission. Therefore, I can look into the uh, the interaction of infected and susceptible ones. Okay? And again, the rate of infection is dependent on different factors, like maybe if you get a population uh, wherein most of them have higher resistance, then the value for transmission rate will be different. Okay? But in this assumption, the simple ones assumes that uh, all the humans in that particular uh, compartment will have the same characteristics. Okay, so when you look at those assumptions, then what we can do now is look at the diagram, or rather construct a diagram and look at the dynamics, okay, by representing it as the rate at which the population changes, okay, or a particular compartment changes. Hey, here, let's look at a very simple diagram wherein I consider two compartments. I'm looking at S. So you have a square where I just look at it as the set of humans in that compartment. And then the second compartment is infected. Okay. So I am looking at a particular disease wherein uh, you have compartments which are either susceptible and infected. Okay. And from this diagram, you can now try to consider where you have arrows going in and going out. So in the first box, I have two arrows. One is going in, so it can be what you call the inflow, okay, of humans into that box or in that compartment. The up arrow going up can be caused by people either who dies naturally, okay, or other factors like getting out of the uh, particular population. So it's possible that if you are looking at a particular area, then either it moves out, okay, due to disease, or just simply migration. So the movement of humans out of that box. Okay. And the other one is when you look at the movement of susceptible into the infected compartment. Okay. So this occurs where when a susceptible person gets infected. Okay. So you now have the interaction. Okay. So once I get to the infected compartment, then I will either have one arrow only going out, meaning either I die, okay, naturally, okay, or I die due to infection. Okay, so again, this is just the simple ones wherein you can divide the arrow into two, where you separate them. Now, in this equation that I am looking into, you have S dot, meaning it's the rate of change at which the susceptible population, okay, changes with respect to time. And I dot is change of the I population with respect to time. Okay, so that denoted by ds, okay, over dt, and di over dt. Okay, and it can be formulated as either, as I've mentioned, lambda is either your natural birth, okay, or other factors that you consider that goes in to the susceptible class or susceptible compartment. Okay, minus mu s, mu there is again either the outgoing, not going to the infected class, but due to natural death. So I can now label mu as natural death. Okay, so death due or naturally. Okay, and then the second term minus beta si, meaning it's the transmission. Okay, meaning it's the movement of susceptible to the infected class. And again, this b beta s sub I can be interpreted in several ways. Okay, so you can divide it into uh, an equation, or you can have it as time dependent, or you can have different ways of making beta sub I interesting, okay, or closer to the problem that you are dealing with. Okay, So what I'm trying to say here is the movement of susceptible to infected, as I've mentioned earlier, can be due to either the age, if you want to incorporate age also into beta, or uh, some sort of resistance of a particular person, meaning you may have people with comorbidities and everything. Okay, or people are that are more social, outgoing, can be also incorporated in that term or in that parameter. Okay, so the second equation, which is delta I, or a derivative of I with respect to t, okay, is just the inflow of the susceptible. So the humans that are moving from susceptible to infected is again uh, the humans that gets into the infected compartment. Okay? The second term, delta I can look at delta to be due to uh, infection or death due to infection, or possibly removing uh, humans, okay, putting it in quarantine. So it depends. So what we're trying to look at is just the outflow here of uh, infected humans. Okay, and minus mu could be your natural death, just like in the first compartment, which is represented by mu. So here we just look at a very simple one, okay, and try to model and study what happens here. Okay, so what you were interested with is to really solve S, meaning the function that defines S is the number of susceptible humans at any given time t. Okay, so you can try to look at the explicit solution to this problem if it's possible. Okay, so another one, maybe as I mentioned earlier, I can have a movement from infected to susceptible class. Okay? So it means that uh, once I get infected, then I don't recover, meaning, so we're looking at a very short time here where I can have movements from infected to susceptible right away. So I don't either recover from it, okay, meaning once I get to, it means that the recovery stage can be removed and put it back to susceptible. Okay, so in this case, we can have this diagram, and following the same previous model, which is represented by Si. If I maintain those parameters, then I will just add a third, or rather another parameter, nu, okay, where nu is just the transfer rate of infected humans into the susceptible compartment. Okay, so I have a plus mu here, meaning the arrow getting into the susceptible, and then minus in the second equation, meaning the transfer of infected humans back to susceptible. So you now have this kind of equation. So here, once you have this equation, then we would like to study the dynamics of this disease, meaning is there a way wherein you can get rid of the disease, or is there a way of determining where the disease is still present but doesn't infect the whole population, okay, just a portion, and as you move through time, then the presence of the disease is still there, okay, or is there a way of to eradicate the disease? So those are the things that we would like to look into, okay, and what parameters do we have to control, okay? So those parameters are the the parameters you have incorporated into the model. Hey, for this problem, what we can do is make it simple as possible, meaning suppose we assume that the total population is fixed, meaning it's just the sum of the susceptible and infected. Okay, so it means that you have preserved the population. What gets in is always balanced by things that goes out. Hey, once you get this equation, then what we try to do now is there a way to solve explicitly S of t? Okay, so unfortunately, due to your nonlinear term here, then somewhat difficult uh, to solve. Hence, what we can now do is study the dynamics of the whole system. Okay, if I were to look at several tools that we have learned in one of our courses, like calculus and elementary differential equations, you were taught on how to make use of different techniques. So if I were to look at a simple differential equation, then the tools that I can get hold of are using the concept of introduction, or rather is trying to identify if it's separable, okay, or try to multiply an integrating factor, or other tools that have been uh, mentioned, okay, in your course. So if those things doesn't work, then what do we do? Uh, then we can try to resort to numerical approach. Okay, here we will now try to see the dynamics of the two compartments, susceptible and infected. And again, some rules will be of help when we try to minimize the number of parameters, okay? Because minimizing or lesser parameters will be easier to analyze, okay? And in this case, what we can now try to do is to solve the uh, two system, meaning we look at the fixed points. So we try to solve fixed points because fixed points are uh, values at which the two compartments will approach through time based on those parameters. And if I were to solve this one, then I can make some representations where I will be able to reduce it in terms of less number of parameters. So as you can see, if I were to solve it directly, what I can do, since I want to solve an equation where the second equation can be taken into account, and try to put in the value, or rather re- replace s into the replace s in the second equation. So if I were to replace s in the second equation coming from the first one, then I can come up with the equation I dot, which is equal to the expression a minus beta I times I. So you now come up with some function in terms of I. Okay, so uh, if you now have a polynomial of degree 2, then what you can do here is try to solve this equation. Okay, so here what we are able to do now is to come up with an explicit solution. So we can have an explicit solution to this problem, okay, by just uh, working with this one, okay, and be able to come up with the solution for I and S. But as you can see, this can only be done when you will go back to the equation here, where this is the polynomial of degree 2, and I can make use of uh, or it's a way of solving this one is uh, going back to your calculus where I just have to integrate both sides, okay, because this happens to be a separable equation. Okay, so coming up with that problem, then I am able to come up with the explicit solution for S and I. So simple as that. But again, uh, not all models or equations that you will be working with is uh, easily solved as shown here. Okay, because we just only have two variables. At the same time, uh, you have initial conditions. Okay, so from there, the usual approach would be once you get to look at the fixed points. So in here, you will have S star and I star. Okay, so the two fixed points can either be the presence of the disease, meaning the I part, okay, is non-zero, or when you have zero here. Okay, so these are the only fixed points that you can come up with. So it's nice because we are able to solve explicitly. Now, if you have three, then it's possible, but it makes it more complicated. And the tools uh, or familiarity or doing them on your own, uh, starting with two equations would be of help because, again, you will see the pattern on how you would solve for the fixed points. Okay, for three, uh, more difficult, but you have to look at different tools to work or to use. Okay, so here we are now able to study the dynamics of the fixed points. Okay, so the fixed points will be represented by S star and I star, meaning this first one is the presence of the disease, meaning it's an endemic, meaning you have the disease present, okay, through time. And here is the fixed point where the disease dies out or infected compartment or infected humans dies out, okay, meaning endemic or this, sorry, this disease free. Okay, so from there we can now try to study and look at the parameters that were integrated into the problem. Okay? And you will now see that if we are to look at the representation of alpha, or rather A, which is just the value here, okay? Okay, so assumption where the sum of lambda and nu, okay? And you will see here that beta is just the concept of what you call the uh, infection rate, okay? So I can call beta as the infection rate, and in this part, so A is just the sum of this, which can be later on simplified if you just simplify the whole thing into a model where you have two terms. This can be uh, looked at as the recovery rate. Okay, so again, the equilibrium points can be studied where if I take the ratio of this, then this will determine the dynamics of your disease. Okay, the dynamics of the disease, and you will see that this is also the basis of what you call the uh, number of new infections that arises, okay, from one infected individual, which most of the people or most of the thing that we now hear is the reproductive number, okay, or the number of new infections. And you will also see that it is sometimes interpreted as a ratio of the infection rate over the recovery rate. Okay? So if you have more infections over the recovery, then you will see that you get to have infected people grow. But if you have the ratio of the infection rate over the recovery rate being less than one, meaning you have greater value for the recovery, then it's possible that you come up with what you call a uh, uh, number which will come up with the fixed point. Okay, so the uh, the reproductive number is very important there because sometimes you can look at when you are able to reduce R naught to one, then you are able to control the disease. Okay, so here is just a simple simulation, and uh, it's nice now to use. So I use GeoGebra here just to make sure that some can play around with the dynamics using GeoGebra. Okay, so before, unfortunately, it was not able to do this, but uh, due to active people working on GeoGebra, then they were able to integrate some functions that also uses concept of calculus, where they had some ways of solving integrations and differentiations. So uh, just to give you an idea on how it's being done. So what you can see now here is a graph where you can look at a simple SI model, and beta here is rather the infection rate, meaning the beta is the transfer of infected humans to susceptible, or rather the transfer of susceptible to infected. Okay, and I use gamma. Gamma is just the recovery rate. Okay, so if I were to look at these two parameters, then I can see that if I start with an initial population of around 20%, so what I did was to make n equal to 1 so that it's easier to interpret. So if I have the total population is always constant, meaning any given time t, it's always equal to 1, then if I start with an initial population wherein I have zero point 0.2, and the susceptible will just be the difference, which is zero point 0.8, then I can now see the dynamics of the susceptible and infected, okay, and track its value through time. Okay, so I just ask MATLAB, or rather, I'm not using MATLAB here anymore, just GeoGebra to take the antiderivative of this. So uh, what is also nice here is you don't need to uh, learn the programming aspect because, again, what you would like to do is at least visualize what's really happening in the system. Okay, so there are also online uh, ways of solving this one, or visualizing this. But uh, in here, what is nice is the concept of a slider where I can change the values of the recovery rate and infection rate using a slider and see what happens in to the time series of your susceptible and infected. Okay, maybe just to shift and show you only uh, how it's being done. Let's see. Uh, can I shift? Let me just uh, put in GeoGebra. Uh, yes. I not. Okay. Okay, so let me share uh, the GeoGebra here. Okay, can you now see the interface of GeoGebra is an open source, and again, it is able to have several tools already. So here, it's just writing down the equations. Again, as I mentioned, you need to know those equations, and you can play around on the dynamics of uh, this one. Okay, so here it will just plot the time series of S and I, okay, wherein you have sliders for beta. So if I have the uh, transmission, or rather infection rate, okay, be increased, then I can see that the graph would also change. Okay, so I can now see also where R naught is being computed, because in this case R naught is just the ratio of the infection rate over the recovery rate. Okay, so that's it. And if you will see now that if you have to play around with the animation, then you can see that you can try to animate and change the values of this one, okay, and see what occurs here. Okay, so what happens here is you have an animation where I'm trying to uh, visualize the dynamics as t changes from 0 to 50. So you now have a time series for 0 to 50. Okay, and what is nice also is you are able to uh, see where you can have the point where the graph of S and I would intersect, or at what point will the shift in the population of the susceptible and infected. Okay, meaning you have the change now where I is more than the number of uh, susceptibles. Okay, okay. So let me go back to. Okay, so that's how I visualize, and also maybe a way of motivating yourself to see what's happening in the dynamics of the model. But if you want to have more control, then write it in either a tool, a computing tool. Okay. So next is an SIR, simple SIR model, where again you divide it into three. And from the diagram, there's a flow from susceptible to infected, and then from infected to recovered. Okay? And I will label them as B, meaning it's just like your infection rate, okay? The movement of susceptible to infected, and then R, meaning compartment where it's the recovery rate. So you now have incorporated where the compartment of recovered humans are taken into account. Okay? And this one, meaning you can look at this model where once you recovered, then you don't get to have the disease anymore. Okay. So in this model, again, we come up with certain assumptions, and the assumptions are again a way of defining your equations. Okay? So the contact between susceptible infected, okay, and you have what's called beta, which is your uh, contact coefficient, or later on we can look at as the uh, infection rate. Okay, so the movement of susceptible to infected, and when infected members leave the compartment, okay, then meaning you have R, the transfer of infected humans to R, which is sometimes your recovery rate. Okay? So simple as SIR model, then you have three differential equations. And we assume that there's no entry from the population. So uh, there's no arrow from outside S, okay? And there's no outgoing arrows from each of the compartments. So this can be modeled or can be considered in several diseases. Like you can look at a simple what sore eyes, or rather chicken pox maybe. So if we assume that once you get to acquire chicken pox, then you get to acquire immunity. Okay, but I think some say that once you had the chicken pox, you cannot anymore. You can still have chicken pox. But for me, I think once you get to have chicken pox, then you're immune already. So we can look at it as SIR. Okay, and there's no disease deaths and it's due to the infection, okay, or natural death here. So we're just looking at the possible dynamics of the disease. Okay, what are the steps again? Again, you just construct uh, just like what you did in the model of a simple SI. Okay, and then the importance of the diagram is a way of checking your equations if the equations will be able to contain all the arrows, okay, for inflow and outflow. And it's also a way of trying to check and later on incorporate alterations, meaning modifications or tweaking. Okay? If you want to incorporate other parameters or come out with another compartment. Hey, similar to the previous one, so simple as uh, if you look at the susceptible population, and if I have transfer of susceptible to infected, then you can look at minus, meaning the outflow, and then from I, you have an inflow and outflow. So you have two terms, and then the third one will just be the inflow. Okay, so this is a very simple SIR model, and this is also the basis where if you try to play around with this one, then it gives you an idea on how things should be done. So how to solve them, how to visualize what's really happening, and get an idea on time series. At the same time, generate graphs so that you can translate those graphs and interpret them into the real problem that you're trying to model. Okay, so that's what I'm trying to illustrate here when we considered the real world transformed to the math world. And then once you have a solution, check if it satisfies and possibly a solution to the real world problem, and then uh, make some tweaking, formulate again the problem. So it's the vicious circle that I shown a while ago. And similar to the simple SI, you're interested on the dynamics, possible time series. If you can solve it analytically, well and good. But if not, then it's just a way of trying to describe the dynamics of the disease or the system. Okay, so uh, just like in the previous uh, demonstration a while ago, this is again to make use of an open source where GeoGebra is a way of visualizing again the dynamics of this differential equation. Okay, and again, I just had to input the terms. Okay, that is why the equations are very important, and because once you have those equations, then you can make use of certain tools or make your own code to solve. Okay, and I forgot to show you a while ago uh, how you would just simply put in the equations into the problem. Okay, so let me again shift you to GeoGebra. So you can just download GeoGebra, and uh, from there, let me show you again. Okay, so once you have constructed the two equations, if you are able to follow the construction, then it's easy also to construct the third or the next one when we make use of. Okay, so here, as I've mentioned, you now have three compartments. Okay, and if I click on this one, this is the formula where, can you now see? You have the formula for a function of I naught. Okay, it's just as we have seen in your derivation in our presentation, it's just the interaction between susceptible and infected, and then the movement of infected to recovery. Okay, and then this one is just R times I, and this one is just again the first equation, which is the movement out of the susceptible class. Okay, and you can have the initial conditions. Okay, uh, if you want it to be more what do you call this, user friendly, then you can put a term where I can change the initial condition. Like this would be I sub 0. So if I change it to, let's say, 0.2, then I can simply run it. What happens is it automatically changes, okay, its values. Okay, and again, use of sliders very important here. And if you want it to be more interactive, then you can have the, what do you call this, the animation to be switched on in here. Okay, so it's all in there. This is where you put the equations. These are the variables. These are the parameters, and these are the uh, points that will be able to generate the graph. Okay, so again, here, if you want it to be more uh, active, then you can have an animation for this case where I can change and see that at some point when will we have the disease, okay, tends to go up, but at some point goes down. So it depends on what you call the values of your uh, transmission, rather the infection rate and the recovery rate. Okay. Okay. So going back to that, you now see a way of analyzing what happens when the reproductive number is less than 1 and reproductive number is greater than 1. And the value R is again a very important number that you would like to study. What factors or what parameters will you perturb, or rather play around with, or try to control in such a way that you are able to control also the value of R naught. Okay, and think the usual things, you can now make it more interesting and come up with your own model. Okay, so based from these basic models that you have uh, constructed, then what you can do is try to put in additional factors, okay, that would be more closer to the problem that you want to solve. And here, just the different models that they try to study. As you can see, the simple SIR model is a way also of modeling uh, COVID-19. Okay, so some are working on these different parameters here. Okay, wherein those parameters, especially uh, the nonlinear term here, okay, the uh, infection uh, rate here is being modeled where it can be some function that you want to work with, okay, or it's a function that could be closer to the data that you are able to uh, generate or observe. Okay, but again, data points. If you have a function here, then it is interesting if you are able to come up with a function that would rather illustrate the infection rate, okay, or other parameters in here. So you will notice that again, in a disease, the transfer or the infected compartment is very important because the arrows that gets in and that gets out in that compartment is a way of controlling the disease. Okay, so whatever uh, expression you come up with, okay, that represents the inflow and outflow into the infected compartment is a way of deciding which parameters, okay, would you like to control. And I think motivations for new models, as I've mentioned before, in my study, I tried to look at age. Now you can have additional compartments like temperature, or you can also have time delay. So let me go back to the SIR model wherein uh, the movement from the infected to recovered is recovery rate, but we can look at the movement from recovery rate to what do you call this, or the movement from infected to recovery rate could be interpreted as some sort of delay, meaning uh, you recover, and once you recover, you move right away to the susceptible class. So that stage can be considered as a delay. So you can deal with the delay differential equations or whatever compartment you want to work with. Okay, so that's another approach where you can uh, or Professor Colliera is an expert of. Okay, so again, in this paper, what we did was just to consider age structured. So as I've mentioned, age structured, I just deal with the compartments divided to susceptible humans where I divided into two. Okay, so why malaria? Malaria was again a vector which is caused by a vector. So in that case, it makes it more interesting because you have another compartment where you try to compartmentalize the vector population. Okay, because the vector population is again very crucial in your model, since if you have the vector population, you are able to control the infected vector, then it's a way also of controlling the disease. Okay, so here if you incorporate uh, age in the human structure, meaning divide the humans into two. Okay, so the basis or motivation for this study was it has been observed that uh, you have larger deaths due to the malaria when it's or on ages 0 to 5. Okay, so and what we did was to gather data where most of the data that are seen or can be accessed is data from South Africa. Okay, and also why do they have a better data storage there? Because some people are able to fund those studies for construction of database or rather data storage of data. Okay, so it's still a project of Bill Gates where it supports the or funds the malaria study. So again, maybe just to uh, go quickly on the process of doing that particular study. Again, you try to divide it into compartments. So the susceptible humans, infected and recovered. So you will see now that the simple SIR model is just extended to dividing it into two again. So you have 6 compartments. Okay, and the vector population is divided into uh, 2 compartments, meaning the infected vector and the susceptible vector. As I mentioned, you don't, we assume that here the model, you don't get to acquire the disease. There's no direct human transmission, but rather through a vector. Okay? So blood transfusion is assumed that this one, you'll not be able to get the disease. Okay, that's why you model it with the uh, use of the vector. So the vector here is the most dangerous animal in the world, which is what you call the mosquito. Okay. Okay. So here's the compartments, and as again I mentioned earlier, constructing the diagram, drawing some visuals would uh, facilitate on how you would construct your equations. Okay? So the different outflows and inflows will now be incorporated into your model. So if you have labels there, then it's also a way of checking if you have incorporated all the things that you have in the model. So the dotted arrow is the interaction between susceptible and infected, okay, and then susceptible and infected here. Okay, okay. So they you have different parameters, which I will not uh, discuss anymore. So again, it's up to you to construct your own model when you try to study some uh, diseases. Okay, and when you construct the model and the parameters, then you try to what do you call this solve. Okay, and do a similar analysis based on the simple SI model. So again, let's go back and go to this. And then another model that we worked with is the modeling of cysto, wherein again, is just a simple SEII model. And this compartment is just a compartment which affects your, I'll call it the infection rate. So this infection rate again is uh, modeled by this. So this is where, as I have mentioned, you can do a lot of modifications when you integrate certain conditions in the model. Okay, like in the COVID-19 model, some papers are looking also at the different expressions for this. Okay, so it's the transfer of susceptible into uh, the infected, or in this case, exposed. Okay, and I think that's where you can also integrate. If you look at COVID-19, then maybe that's how what the different protocols are being incorporated or being used. So if you have a situation where you really implement strict protocols, then possibly you are able to control the movement of susceptible to exposed. Okay? So if you have a simple proportion only, then That's again the uh, infection rate that we would like to study or we would like to look at. Okay. Hey, I think I still have 2 minutes. This afternoon, we will try to show how an agent-based model is used. Okay, and you will see how uh, what you call this these models. Okay, uh, is used to at least have a visual maybe aspect of what's happening in the disease. Okay, so the idea behind this modeling is for a person like if I were a decision maker and a mathematician would provide me values or numbers, then sometimes I am not able to appreciate it because I don't see really what is happening. Okay, so what one way of convincing maybe some decision makers is to make use of visual aids, okay, because it's some way of laymanizing the things that uh, you are doing. Okay, so uh, in the math world, what we can do is try to give them a visual uh, way of interpreting what we do, okay, so that they should be able to appreciate the importance of what you are doing. Okay, uh, I have seen if you are to simply look at the equations and show them and say that these are the numbers, these are the values, this is the dynamics that occurs in the model. Uh, uh, Sometimes for lay people or lay people which would be making decisions would not really appreciate and uh, would not really appreciate what you're doing, but it's a way of convincing them at some point. Okay, so this afternoon we'll try to give you an idea on how agent-based modeling software is used. Okay, and you don't have to know the software right away. So in case that you have computers with you, then I hope you can download them because it's an open source. And once you download it, there are certain models that you can tweak. Okay, so the fastest way of learning things is to make use of existing models right away and play around with those models. Just like when we try to do this is modeling, meaning I should first start with a simple model and then try to understand how it's being formulated, try to solve them, meaning making use of tools that I have learned. Okay, uh, and once I try to do them in a small scale, then I am able to understand the dynamics or how it's being done, and hopefully do the same uh, approach in a more complex system. Okay, so as I as they always say, start with the simple one. Okay? So you have several open source or agent-based models, which is really used in the business world. Okay, most of this agent-based modeling were really used by decision makers, okay? Because they were able to appreciate what could be the impact of the decisions that they would do if they have a visual uh, perspective of what would happen. Okay? And here, there are several uh, packages where uh, some packages are dedicated really to specific uh, problems. Okay? So, like for example, for Swarm, it's a general purpose agent based. For uh, Gamma, how Gamma is GAMA. So it's a GIS agent-based modeling architecture, and it's using GAMAL, or what you call this GAM language. Okay, and a very popular agent-based being used in the different field is NetLogo. Okay, the again NetLogo is some sort of uh, similar to Gamma. Okay, and it's also being used in different fields. Okay, and what I'm trying to show here is choice, or rather, yeah, a menu of different packages that you can try to uh, download and play around with. Okay, so maybe I will first uh, stop here. Okay, so if you have questions, maybe we can entertain a few questions. Okay, so at 1 p.m. we now start and play around with the agent-based modeling package.
Okay. Thank you, Sir Joel. Do you have any questions, guys?
You can ask any question, especially maybe uh, I hope I made it as simple as possible. And again, those are the things that we usually do. Okay, uh, but the aspect of deriving and studying them uh, would be uh, a track that some of you can do. Okay, some maybe um, this, for me, as they have mentioned, if most of the people in the bio or in the other fields will just make use of tools, and those tools would be of help, okay, to visualize, and you will ask people in the, or rather mathematicians, to help you out for the formulation or derivation. But I think you can try to contribute by just trying to do some models, okay, to understand and how it can be solved. Oh, tanong?
Mukhang wala yata, sir.
Okay. So I hope, siyempre yung mamaya, ano ba, I think on this track, most of you are able to do Java programming, right? So they had an idea on how Java runs. And again, huwag kayong matakot. Siyempre, iba, tawag ko Javaero. Pag sinabing Javaero are people doing really Java. Okay, so I have friends wherein, they really work on this language, and it's they appreciate what we try to do in the math, because we are able to share uh, the modeling aspect, and it's up to them to do their part and share their results with us. Okay? So what's nice here is Java is some sort of, I'll call it as a front end, okay? Because it can easily give you some visuals, especially on the net, okay? But I think early 10 years ago, it was a hot uh, language, but unfortunately, due to security problems, uh, some are really looking at the way of solving it. Okay. Okay, walang tanong. O simple yung modeling aspect lang naman, di ba?
Okay, ata sir. May...
Tulog na lahat. O, sige.
Okay,
So I
sir.
hope.
Thank you so much for
Thank you for sharing. Okay, so I'll see you at 1. In case, yun nga, yung iba naka-install ng, maganda kung na-install nyo kasi meron na siyang built-in packages that we'll play around with. Okay? So maybe some of you are more familiar with it. Okay? So see you again this afternoon. Thank you for listening and for your time.
Thank you, Sir Joel. Okay. Let's resume at 1 o'clock. Thank you, guys. All right, lunch break muna po tayo. All right. Good afternoon again, everyone. I hope you're a bit rested and you've completed your lunch or something. While waiting for our lecturer, may I please flash again the MSP, the MSP membership Google form, so that if you wish to be a member, you can register. If you have questions regarding the membership, please do not hesitate to email us or message us and we will get back to you. There you go. You can screenshot and I'll be um, mhm. Okay, so you'll find a link in our, I pasted it in the chat box regarding the registration form. Please take note also that you can register before May 15 because the annual convention for MSP will start on the 15th of May. So you can, we encourage you to join if you want before May 15. Okay. Other announcements, we will be giving the link also for the evaluation for Professor Adawe after his lecture. And after that, after the break in the afternoon, please also join the plenary talk of Professor Isabel Adawe. and the closing remarks to conclude our SINSM 2021. Okay. I hope if your laptop permits, I hope you were able to download the Gamma for the demo session so that you can actively participate during the demo of Professor Adawe. So I think he is Sir Joel. Are we good now?
Yes. Can you
Okay.
hear me?
Yes, sir. All right, over to you.
Can you now let me check so I won't be sharing my I will not be sharing my video. So let me first check if anybody who were able to install Gamma on their terminal. Can you maybe just a reaction thumbs up in case you did? If not, then maybe we will just have to show, or I will just have to show the features and show you uh, things that can be done, because as I have mentioned earlier, learning Gamma would be quite difficult in the first few uh, sessions. As I will say, it requires a steep learning curve, okay? Which means first few things that you will do will give you a headache, okay? So anybody who were able to download Gamma? That anyway, so Gamma is again an agent-based modeling package, and it's open source, meaning it's free, and it's a collaborative work of contributors. And I will now share, maybe it's better to share the Gamma once you install it. Uh, and or successfully install it, then you just have to play around with it. Okay. So the first time I installed it took me not really a few minutes, but a few hours. Okay. Unfortunately, I'm running um, Mac, which is more difficult to configure. Uh, and you really have to spend time, especially if you have version incompatibilities. Okay. So hopefully for you who will be installing them on their own computers, I hope you have a smooth way doing it. Okay. So let me share first. I need to run Gamma. Okay. So Gamma, some sort, requires a lot of space and computing power. Okay. But I think even if you have a 16 processor computer in the group blog, not yet able to what you call this, make use of multi-processing computers. Okay. Okay. Let's see. I'm not sharing. Let me close first everything. Okay. Okay. Wait. You. Sorry. I need to. I think I can share the whole screen. Pwede pala. Para makita nyo na lang. Let's see. Let me check if that's possible. Okay. Oops. Wait. See, I'm having problems also. So that's the problem with this version. Okay. Wait, let's see. Can I share? Ano nakikita nyo? Stop share. Can you see now my screen? No.
Hindi po, sir.
Anong nakikita nyo? Wala.
Ano lang, sir, parang Joel Adawe has started screen sharing pero yung screen po mismo ay hindi po namin nakikita, sir.
Yuck. Stop share. Okay. So let me share. And then, so what do you see now? Can you see my desktop?
Black pa rin, sir.
Ah. Ano lang. Ayan. Yan.
Yes, sir. Okay na po.
Okay. So I think if you have attended the first few sessions before conducted by Sir Lee, was able to show you how to make use of. Okay, so once you install Gamma, I'm using version 1.8.1. Okay, and if your computer is of lower version, I think there are some compatibility issues. Hence, you resort to install version 1.8 or 1.6. Okay. Okay. So once you install the package and then you have it run, this is the default thing that you will be able to see. Okay. And uh, there are what you call different parts, and what is important is when you construct your code, it will require you three sections. Okay, basically the four sections, no, not yeah, three sections you will need to have. Okay, so it's like your main program, and then your uh, species, okay, and then your experiment. Okay. So agent-based means that each point or each individual is considered an agent. Okay, and a particular agent will have certain characteristics. And for those agents, you can define how it will move. Okay, and when it moves, then it can be what you call this controlled, okay, only by the defined what you call these functions that you have in Gamma. Okay, so it is a continuous package that is being developed, and it has several versions already. And recently, uh, if you look at its web page, let me check. Uh, So if you try to Google Gamma, it will show you the website of Gamma. So you can try Gamma for agent-based. Okay, so you just have Gamma agent-based modeling, and you will be directed to Gamma platform, and you can see how it's being uh, constructed, or you can have uh, references on how to install and then learn, and then a little bit of the blog. Okay, so maybe before I let me just stop share again, and then I will show you. I should have shared the whole screen of my so you now see the website for Gamma. So it's Gamma platform github.io. So if you will see, you can download here. Okay, and when you click download, then you can have the different versions found here. Okay, so under Windows, under Mac, under Linux. Okay, so can you are you able to see what I'm trying to share? Right, the website of Gamma. Tama ba?
Yes, sir.
Okay, so uh, and if you look at the documentation, it's here. Okay, you can download it. I think it's around 1,000 pages. Okay, but it gives you the details on how to install, how to use the interface and everything. Okay, so me, I usually when I play around with it, I go straight and then try around the examples. Okay, so the best, as they advise, the best way to learn it is to try those examples right away. Or if you want, you can follow the tutorial. Okay, so here you can have what you call this learn, and it contains the different tutorials. Okay, so the difference here is if you follow the tutorials and you are not able to configure your folders correctly, then you might get lost. Okay, so what's nice here is It gives you actual screen captures of what your examples would look like once you run them. Okay. So here, what is nice is you now have a predator prey road traffic, 3D flu, which is my basis, the disease dynamics, incremental model, and some BDI architecture. Okay. So in this tutorial, I think you now have an interface where this is the actual thing that you will see when you run their examples. Okay. So as you will be noticing here, it makes use of recent development like the 3D versions. Okay? So the 3D tutorial also is contained in here. But again, the using the 3D tutorial requires you to download some images, and it requires you to have images uh, that are stored in or captured by GIS. Okay, so if you are to look at shape files, then these are files that gives you uh, XYZ coordinates. Okay, uh, of a particular what do you call this image. Okay, and as you can see here, this is the basis of uh, modeling traffic at the same time diseases, wherein diseases are seen in terms of agents, okay, moving along roads and buildings. Okay? Again, the difficult part here is to construct shape files. Okay, so I tried to construct, or rather download, the shape files of Baguio in particular using OpenStreetMap. But once you download, especially the graphs that it generates, like road maps, okay, sometimes when you look at the road maps, some uh, so you're looking at polygons, okay, meaning lines, and so once you look at the polygon, some of those polygons are not contained in one, okay, figure, meaning it's somewhat disconnected, and sometimes you have difficulty uh, simulating the roadmap due to discontinuity on those shape files or on those polygons. Okay, so what I'm trying to say is, like, if you have a triangle, then that triangle should be constructed by one only. It shouldn't be what you call this two sides and then the other one is separately done. So if that happens, then sometimes the way of the agent to move from one point to the other point, okay, will have problems because you cannot go to the third side, which is not part of the first two sides. Okay, so it will be identified as as a different road. Okay, so what happens is some will have to clean, okay, the graph. That is why just to give you feedback, I was wondering why the people that were working on the maps, which was I think headed by Dr. Chelo Pasqua. They had to clean maps that are what do you call this, generated by satellite images. Okay, as you can see, when you download the shape file, it gives you a rough graph, but as I mentioned, the shape files wherein the polygons are some sort of uh, not connected, okay, meaning different uh, polygons, okay, meaning different. what polylines, or we'll call it polylines on one figure. Okay, so if I look at this one, again, documentation of this is it can be seen here. So you have multiple applications, and what is nice is the recent uh, uh, group that are working on this, especially during the COVID, and they are now trying to integrate uh, concepts wherein the disease dynamics uh, being considered using gamma. Okay, especially their study uh, in COVID. Okay, so I think you can look at changes from 1.6 to 1.8. Okay, and then you can have what you call this, a way of learning the they call it gamal. Okay, so it's the gam language. So if you look at this one, and you will have an introduction, as you can see here. So it takes some time to really look into. Okay, so the different parts of the language, wherein again it's looking at the species or some agents. Okay, and uh, to start it is just click on Gamal, and gives you this one. So this interface also is seen, okay, as an HTML link in what do you call this, in the when you run the Gamma. Okay. Okay. What I want to? So if you look at this one, I think this is the different parts that I was mentioning here: the model, okay, and then the species declaration and the experiment. So it's just like writing your own first code in any language. Like, let's say, if you're looking at C or MATLAB or Python, okay, it has a similar structure. The only difference here is to look at the syntax. Okay, so for any language that you will try to work on, it boils down to familiarity of your syntax. Okay. Uh, this is a high level language, and what is the disadvantage here is if you will be simulating and doing uh, computations, especially numerical computations. So it's not advisable to have uh, the uh, the computations done, okay, uh, in what you call this, uh, real time, but rather it should be done offline, meaning it has to have a uh, back end to do the computations, just like the contributions recently provided, like the use of uh, uh, numerical solvers like ODE. The concept of ODE was recently incorporated, where the built-in functions are a few only. Okay, so RK4 is the usual uh, approach, and and when you deal with the heavy information, then you will have difficulty computing it, or maybe visualizing it. Okay, so it can handle, they say that it can handle a million agents. Okay, and I tried only a few tests, but it takes some times to really see uh, the output. Okay. Okay, so I think you can try to follow this case wherein you have to construct this one. So you have the model, which is the usual what do you call this, uh, code of your the file, or the name of your code. Okay, so name of the model usually is the same as the file name. Okay, and then you can have you can import some files like Excel files, or other files that you need to process. Okay, and again, after that is your global definition of attributes and your species. Okay, it's how you define those species, if how they would move. Okay, the type of uh, agents that you will be representing, and then the attributes. Okay, and then the experiment will be usually the things that uh, the agents will do. Okay, so it's like your simulation uh, uh, part. Okay, so as mentioned here, the basic skeleton is this one. Okay, so name, go global, species, and then your experiment. And from there, I think you can start and uh, follow and run the what do you call this, the examples. But what is important again, especially when we deal with uh, computations, require some computations like the discussion in this morning's lecture, where we need to solve numerically particular equation. So, like for example, if you were to integrate, uh, then you will have a numerical approach to do the integration. Okay, and that will pose some problems because, as I've mentioned, uh, it will be doing some computations wherein this only deals with some sort of the uh, agents. Okay, so when you have a particular agent and it is to move, okay, based on certain computations, then you have difficulty. Okay, like pre-processing should be done. Okay. Okay. Ano pa ba? I think that's, if you have time, please download the PDF file. Okay, and uh, go through uh, doing the exercises or the examples. Okay. So you can see how you download uh, the contributors. Obviously, let's now try to see who developed this. What do you call this agent-based model so package. Okay, as you can see, it's these persons who are the people from uh, your IRD, okay, and usually from this unit. Okay, so University of Toulouse. Okay, so this is Benoit. Uh, when I met this guy, uh, they pronounce his name as Benoit. Okay, so these are the three key people, the four key people who started this ones. Okay, and later on, contributions came from some group in Vietnam. Okay, so they tried to look at the group of who is this guys. Okay, uh, who are also working on the math department, because again the some parts are not, these are not really designed for numerical computing, as they tried to see if it can be incorporated. Okay, and that's why some of it was really incorporated recently. Okay, so it's an open source, meaning you can contribute into the libraries. So it's an ongoing research of different several groups. And as you can see, the developers are the same people who have been working on this package for so many years. Okay. Okay. So ayan yung tutorials. Ito yung download. Okay. Ito yung mga projects. Okay. So if you look at the different projects currently being done, okay, they have this kinds of simulations wherein, again, it's an ongoing toolkit that is being developed, especially for COVID-19 modeling kit. Okay. So they're now trying to integrate use of GIS. Okay. Okay. So um, okay. So let me now proceed with the features of this one. Okay. Where is my shared file? Okay. So the first example that you can do is when you look at an SI model, we try to divide the compartments into two again. So we have mentioned that it's the set of susceptible humans and infected humans. Okay. Now, if you look at the term, going back to the equation initially, how would we compute the transfer of susceptible to infected? So that's what you call, I would look at it as the infection rate. Okay. So infection rate is the number or the parameter that you multiply, okay, to the number of humans that would move to the uh, the rate at which the movement of susceptibles into infected. Okay, and that poses a difficulty because again, this will be computed. Okay, or this should be based on some computation or information. Okay, so again, it goes back to simulating a iterative process. And when you look at the computations done initially, the computations for the system of differential equation would boil down to what you call this discretizing. Okay, so you try to discretize it, and then you do some numerical tools. Okay, similarly here, it's the same, except that when we deal with the actual thing that happens in reality, uh, you will be trying to discretize it. And in particular, since we deal with humans or agents here, then we're trying to look at integerization. Okay, so I will look at it as integerization, meaning the numbers that is being done uh, in ODE, okay, would be floating numbers. But here, when you deal with agents, then it will be some sort of an integer because it doesn't make sense like having one half human, okay, being infected. So uh, to 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 deal with that, then you need to be aware of discretization. Okay, so if you look at the SI model, you will need to, the first property in that model does not uh, the first property, which in this case should be uh, to make use of whole humans or whole person. Okay, so if you look at the iterative process being done in the numerical approach using a tool, okay, then you will be trying to generate sequences, let's say for S and I. So it will be SN and IN. Okay. And in here, to be more realistic, your SN and IN should be integers. Okay. So for example, if let's say my what do you call this? My beta was, I think, used as the infection rate. Okay. Were 0.67. And the other parameters would be what, let's say you will be able to generate, if you look at the iterative process, would be like, for example, if I start with 100 humans, then let's say I start with one infected, and then 99 susceptible. Then if you look at the iterative steps, then what gives or what are generated are a sequence where in 99, then possibly the next one will be 98.4, and then the other one will be 1.6 and so forth. Okay, so in the SI model, we need to change this property. Okay, so what happens is to fixed population size, and the total population size should be again assume constant to for simplicity, and excuse me, we will try to generate a sequence. But the sequence that you generate, let's say Sn, going to Sn plus 1, In to In plus 1, should be an integer. Okay, and it should be true for all n. So if I iterate from S1, S2 down the line, and the sequence should also or should all be integer. Okay, and then when the population size is constant, let's say n, I'll call it total pop, should also be an integer, which is constant. Okay, so this is the fundamental property that we require for the discretized model, which is the basis for the simulations in here. Okay. Uh, for showing that in the SI model, like if you look at the concepts that should be uh, studied first, like the concept of monotonically decreasing for S and IN, okay, it can also be shown also for the discretized model, or I will call it integerized model. Okay, so positivity should also be shown. So you can easily show it by constructing what you call this, the sequence, okay, of susceptibles and infected. Okay, so for you will consider some delta t and then some uh, beta multiplied to delta t, and uh, the results should also follow monoticity. Okay. Okay. So the concept of R0 is the same, but in here it will just be the, since it's a reproductive ratio, then it will be some floating number. But the sequence, as I have mentioned, of the susceptible and infected should all be integerized. Okay. So what are the things that should be done there? Okay. If I were to consider, let's say, the different possibilities, okay, for integerizing when we apply it on a two compartment model S and I, uh, what will happen? There are how many possibilities? It's like if I have two uh, two variables, so two spaces. So if I recall my statistics, then that's a combination of, so if I have, let's say, an SI model, how many possibilities are there? Okay. The things that I need to consider is either the floating point number that will be either rounded off or rounded up, rounded down or rounded up, right? So if I have an integer, it's either I take it being rounded up or rounded down. Okay, so if there are round, I think you can uh, look at functions, built-in functions, or not necessarily built-in functions, but uh, for you to make sure that you either put it to the lowest number. Okay, so uh, like for example, if I have an interval, let's say from zero point 0.5 to 1.5. Okay, so when we round, so the process that we can apply is to round it or maybe let me just show. Let me help myself in MATLAB. So I can use the round or the floor, right? So when I have round or floor, meaning you either round down or round up. Okay. Uh, so I can also have the ceiling. Okay. So when a number is forced uh, to discretize to the highest integer. Okay. Okay. So if I were to look at those types of discretizing s. Okay. So what I'm trying to say is I can have round, uh, ceiling, or floor. Okay. So you have choices like you either round and then you put it to the ceiling or to the floor. Okay. So those are the possible uh, discretized SI models. Okay. So if I have those uh, types of discretizing S, then I have three possible decisions: round, ceiling, and floor. And I have two variables to use there. I have a combination of 3 taken 2. Tama ba? Or 3 taken 3 pa rin. 3 taken 3 times 3. Sorry. So combinations of 3. Okay. And how many choices do I have? A combination. Yeah, I have two blanks, so that's 3 times 3, so 9. So I have 9 possible scenario. Okay, for the discretizing of the S and I. And at the same time, I need to impose that the sum of S and I should be an integer. Okay, so if you look at those different uh, model outputs, only I think 2 or 3. Yeah, I think there are only 3 uh, possible things that should happen there, because again, uh, if you look at the combinations, like for example, if I have an individual which results in the continuous ODE approach will be 67.5, and then the other one is 32.5. Okay, so you can and you should impose that the total is 100. Okay, so you can either round up to 33 and then round up to uh, 68. But if you do that, then that adds up to 101. Okay, so that cannot have the possibility of round up. Okay, so uh, what you will do there is uh, you have to round up uh, the rule. There's the rule wherein I think you will round up the value that is over, let's say, the total over 2. Okay, and then round down the other value uh, which is below total over 2. Okay, so in that case, like for example, if you go back to the first case, the first one will be 32 and its pair should be 38. So if I have 67.5 infected, what do you call this? Uh, 32.5 susceptible, then it should be 68 and 32. Okay, so that's one of the possibilities. Okay, so again, those are the things that should be what you call this emphasized. So the different combinations of the possible, yeah, the possible combinations would be to ensure that S is discretized, I is discretized, and then S plus I, which is the total, is discretized. Then uh, I think the possibilities would be let me check my notes. Floor and uh, equal. So it should be equal to n. So it should be ceiling for S, floor for I, and then floor for S, ceiling for I, and the third one is round, which is equal to n. Okay, but when you have to make use of round, as I've mentioned earlier, uh, you will have to round up for a number when the number is greater than total over 2, and then round down for the number uh, total over 2. Okay, if it's less than. Okay, so I think those are the things that you need to uh, keep in mind when you deal with the agent-based modeling. As one of the limitation is you cannot have one half as the human being infected. So uh, if you will see later on that when you try to simulate the process, then if I start with let's say 99 and 1, okay, then it's possible that the next population will still be 99 and 1, not 98 point something and 1 point something. Okay, so it's like uh, making sure that your model would make use of integers. So you will have simulations for uh, that kind of setup where the time step can still be uh, done. So you can have smaller time step, okay, but take into account that the values for I and S should be an integer. So like for example, if you have a, let's say, a infection rate of 6.67, uh, and then your S starts with 99, I starts with, let's say, 1, then what happens is either you get to 99 and 1, but yeah, it's 0.67, it becomes 98 and 2, and then 97 and 3, and then 95, something like that, and 5. Okay, so it still shows you the same dynamics for uh, ODE approach, except that it will just be generating points. Okay, so you will possibly get similar form, but only an integer form. Okay, but for some cases, you might expect that the the analytical solution would converge to n and 0, which is the equilibrium point. But for the integerized form, it's not necessarily to have n and 0, but rather maybe 99 and 1. Okay, because of those rules that you have considered or have mentioned. Okay, so that's how I would look at the discretization of an SI model. Okay, and from there, I think you can now have an idea why the simulations in some cases in they call this in the gamma package will be what you expect is or what really comes out is not what you expect in the ODE approach. Okay, let me go back now to, okay. So here, again, once I have a simple code here, so I just look at this ones, and again, you will create, and then the number of agents, okay, and the step, okay. So again, if you highlight or hover on that particular item, it gives you a description, okay. So that's as long as you are in the gamma, so you're running gamal, okay. So that's the advantage, like in MATLAB, wherein if you highlight a particular command, then it gives you the features or how it's being done. Okay, so again, the concept here is just to look at species wherein you have a reflex where it's the movement. So if you look at wonder, uh, okay, it's the movement of a particular agent, and here it's random by default. But later on, you can try to what you call this, control the movement, and it can be in terms of uh, what you call this, the direction or some sort of, yeah, the direction means you have a target that it will follow. Okay, and the movement can be bounded, so you can have this one, and the movement from one point to another is in terms of speed. Okay, and that is why I have initially mentioned that the shape file is very important. Okay, because if I will have to move a particular agent from one building to another, then it has to move in terms of an access. Okay, so if there's no access, then uh, what you can do is maybe at random will have a teleport, meaning it will just move from one building to another at random. Okay, but since we're trying to simulate a closer uh, or an ideal situation wherein I will have to move from one building to another by looking at an axis, okay? Which means it depends on the path that you will have to define. So if there's no connecting path, then it's possible that uh, it will just move along the building. Okay. Again, the buildings are should be properly defined. Therefore, its building is identified in the shapefile as a closed polygon. Okay. So the movement will just be allowed within that polygon. Okay. And then roads adjacent to it can be a way of accessing it. And the movement from one point to another, since it uses path, okay, so you go back to the concept of a path from one building to another, you will just looking at the concept of shortest path. Okay, so built-in functions are already incorporated in there. Okay, and then the target, it depends. You can prioritize, so you have to look at the details of the features. Okay, so in this example, let's just look at an initial population. Let's say I have 10 uh, uh, agents, okay? And then I initially have one infected human, and I just try to distribute in a region, let's say, of shape. So I have this one. So you will see that operation for the geometry of the shape should be either square, circle, okay? And it will be just move on this particular shape, okay? So it means that it's like putting them in a room and then put all those agents in the room, and let them move at random. So they wander at random. So when they say they wander at random, they just move, okay, without any particular target. Okay. Later on, what you can do is you can specify how they will move, and specify a particular target. Okay. So it's like if you will now try to simulate, let's say, a classroom where you have a particular exit, then you should define a target so that uh, each agent, okay, will move based on its target. And then you also define its speed, how it will move, okay? And the movement would be uh, in terms of what you call this, speed, okay? And here, define the speed to be 1 plus random 3, meaning uh, 1 to 4 kilometers per hour. Okay, so you can have a smaller, meaning meters per hour. Okay, so this is how you define it. So it's just like a random. You will generate a random from 1 to 3, which is added to 1, which means the maximum speed for that particular agent would be 4, minimum would be 1. Okay, and it's like a cycle wherein you will do it for each agent, and then before it moves to the next. So you call it like the first generation, or yeah, the first time step would be done for all. Okay, and you will have to look at uh, instead of seconds, it will be in terms of cycles. Okay, so it's like the iteration or steps, or I will call it generation. Okay, so if I have this simple code here, then I have initially an initial population of uh, let's say 10, okay, and then one infected person, and they wander at random at any direction, and they will move at this speed, okay, and uh, I will have a condition wherein if the susceptible agent is within 2 meters, okay, 2 meters with an infected person, then I will have to flip a coin. It's like a probability that 1%, okay, if you are in 1% when you flip, so the probability to get infected is 1%. So if you are, well, it's like flipping your probability, and if this is you within 1%, then uh, you are labeled or tagged as infected. Okay. So here, yung flip, this is the case wherein you will impose some values, or based on values like this can be what you call your infection rate. So what's the probability that I get infected if I am within, let's say, 2 meters? So they say that if you stay, 30, that's why they have advisory, if like looking at COVID, then 30 minutes of uh, conversation, okay, with protocols should be the maximum. So uh, uh, doesn't mean that you are assured that you will not get infected, but again, there's some probability. Okay, so this is assumed to be for all agents. So it's like if you have 1%, or you can have 10%, meaning if you have 10%, then that's 0.1. Okay, then it incorporates all the possible uh, conditions, or rather, yeah, uh, attributes, okay, for the infection rate. So it's like looking back at the simple model of an SI, where beta is the infection rate, then beta can be considered as a function. So if you look at a function, then here it would be different, because this, the probability, the flip here is just like tossing a coin. I get infected or not, if I am within, or not really a coin, but pressing a calculator, and you get the probability of 1%, then you get infected or not. Okay, so the values here, what you can do now is instead of a flip, it can be passed to a function, meaning uh, you will compute its probability there, and that will be your basis if that person gets infected or not. In which case, those are the conditions that you might think of, like if you impose stricter protocols, if you have comorbidities, okay, or other stuff. Okay, okay, so I think this is the uh, part wherein very what do you call this? Very important to look into. Okay, because this one is already fixed, but make it more realistic, then you make it or you have a function that defines this flip here. Okay, so the circle is just some sort of your radius, meaning if I am a human person, I think sometimes it's for visualization. So if I have 1 meter, then if your map later on is uh, on a bigger scale, then you will not see the dots or the agents in there. Okay, and uh, this one is just the mapping. Okay, wherein you will just map each agent that moves at random or wander at random on the space provided, which is of this dimension. So if you run this one, then it will generate some sort of the dots here. So can you will see how many dots? 10. It should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 humans distribute or randomly distributed on a grid of 400, square of 100. Okay? And this is some sort of radius. So mataba masyado, di ba? Radius 3. So maganda siguro 1 meter, malaki. But I think for visualization purposes. And it's also important because, again, your region, I think the research of Jonas will have some sort of considering, what you call this, some properties for a particular agent here. Okay. So those things could be incorporated like psychological uh, thinking of a particular person. So uh, those are the things that can be incorporated in your flip. Okay, so if I do the simulations, then it will just move around. Okay, and obviously as it gets in contact with a particular person, then it gets infected. But as you can see, medyo matagal dahil yung probability of getting infected is only 0.1. So as this one is trying to move, so it's like a open space where everybody is walking, okay, at random at any direction, and uh, as it moves around and it gets into not really contact or rather contact within the region, how we call it, it's like your own region where you have imposed in there. Okay, so within 2 meters, then you either get infected or not. So at this one, as you can see, the humans are now all infected. Okay. Okay. So that's the simple. Once you have a simple case here, then what you can do now is, I think I did some. So I the SINSM. So what you can do is you create your own models in here, and then uh, uh, you try to put in the two folders that are required in your model would be the include files, which contains some shape files that you will use. Okay, and here I took several uh, uh, pictures, okay, of Burnham. So I just considered a portion of Burnham, Lakandula, City Hall, Abanao, okay, a part of Session Road. So I just took that image and then take its shape file. Unfortunately, the problem there is once you take the shape file, uh, open by open street map, it creates some sort of, as I mentioned a while ago, polygons wherein some polygons are disconnected. So you will see physically from the graph it's connected, but how it is constructed, it those are constructed by polylines. So what you can do is some cleaning. Okay, so when I say cleaning, then sometimes you might as well rewrite what you call this, the the map. Okay, or I don't know if you have a tool wherein you can try to connect polylines. Okay, so you have layers of lines and then you try to have it as one polyline. Okay, so those are some features maybe can be done by any software Okay, like I don't know uh, if ArcGIS can do it, but I'm sure it can do it. But for the open source, still being explored. Okay. Okay. So the next one is to put it in such a way that I will now try to draw the physical points, okay, of those agents. I think I use SI model 1. So it's the same one, okay, and then I will just have to incorporate the graph that is generated by GeoGebra a while ago. Okay, so similar uh, graph that GeoGebra should generate. Okay, so it's the time series of SNI. Okay, so it's the same except that you just have to uh, work on two. Okay, so here, as you can see, it's smaller points, and then the chart will be the simple SI model where it will try to generate the time series. Okay, so if I were to graph this one, then it will just move as we have shown a while ago at random, and then the chart will just be just what you call this, uh, putting in points. Now, what do you notice here? That's the concept of what you call integerization that I mentioned a while ago. So the value should only be an integer. You cannot have 3.5 susceptible humans, okay, and then 16.5 infected ones. Kaya ganito yung graph. Okay, so unlike in what you call this, unlike in the uh, continuous model we had, it's still discretized when you compute it, but it considers float. But in here, it considers integers. Okay, so you will see that in the simulations, if you look at these points, okay, and visualize them, either is this person should either be an infected one or a susceptible one. Okay, so hindi pwedeng half red, half green. So yun yung kailangan nating tignan. And again, once you have the rules on how you integerize, then and then show certain properties that it's valid, okay, then you can now impose those conditions in the model. That is why I have mentioned a while ago wherein the concept of integerization, wherein you either have to make use of round floor and ceiling. Okay. So, and then after that, what you can do now is try to overlay it on a graph. So parang tinignan natin, random on a region, and then pagagalawin mo, and then visualize how the time series would look like in terms of the solution of the system of equations. Okay, meaning it's like looking at the system of an SI model, and then we had a way of solving continuously. And then since you're obviously it's still discretized, but you use floating point, and then in this agent-based approach, then you will be looking at the population in terms of integers. Okay, and once I have that, then there is some sort of comparison now. You can now try to compare the results of the continuous and the uh, this integerized SI model. Okay. And then I think let's now try to impose. So, ganun, yun yung proseso lang. Dadagdagan natin at lalagyan natin ng shape files. Okay. So, it's the road. and then the buildings. So the buildings, as you can see, will just be closed polygons, okay? And then the roads should also be some sort of lines only, okay? So it's difficult to see if I were to look at the roads, if they are obviously visually you can see it's connected, but sometimes if you look at the details how the shape file would generate it, it's separated, meaning they are constructed by segments. Okay? So pag constructed by segments, parang nangyayari doon, yung isang kunwari, isang line na makikita mo, maya siguro sabihin ko na lang yung triangle na 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 figure, pwedeng i-construct kasi yan as one polygon only, which means different siya pag kinonstruct mo na isang polyline na dalawang edge, dalawang side connected by the third side. Okay? So ibig sabihin, it's possible that I cannot go through the third side when I am on the second. Okay? Because there's some sort of not as one polygon. Okay? So yun lang yung disadvantage. Kaya I was surprised that I need to clean up the roads, but it's difficult to clean. Okay. Okay. So I now look at model 2A. Where's my model 2A? Ayan na. Here. Okay. So it's the same. Okay. So the road network is the shape file extracted from the road map. Okay. So again, I have a file which is this one, and it gets its shape file from the Burnham dot. Am I right? Yeah, the Burnham dot map. Okay. So I tried to clean roads, but it's the same. I have difficulty cleaning it. Okay. Okay. So I think that's the whole process wherein I will now integrate the concept of having buildings, just like in the examples. Okay. And the map is this one. So as you can see, as I've mentioned a while ago, these are lines, but some of them are not really connected. Okay. So if you click on this using the a package which will look at the shapefile, when you want to delete one file, maybe one line or the whole line, it will only delete a portion. Okay, so yun yung, I hope you see or you see the concept behind it. So initially, if I have this, okay, on my map, so I lay down all the, what do you call this? All the in agents, okay? So I have 1,000 of them, okay? And I think how many were, I have 1,500, and then initially I have 100 infected, randomly distributed on that region. So if, let's say, if you want, siguro maganda, palitin lang natin, mahirap makita, mga 50, okay? And I try to see the dynamics of the disease. So again, each agent will have to move at random on a particular target. So it's like at random, it will go to this point or to this building. Okay, so it will go to this building only if it has an access. Okay? If it doesn't, then it will not move anymore. Okay, so and then random again, another round of generation, it will have again random. So it's like a time lapse where each agent will have a particular target, and then it will move or not. And if it moves, if it gets too close to a particular agent, it takes its particular distance and it flips certain probability for infection, and goes again to the next one. Okay?
Okay. Sir, sorry.
Yes?
10 minutes
Yes.
remaining. Thank you.
Okay. Okay. So if you look at the map, okay, makikita mo na-infect almost lahat. But if you look at, this is along, I think, yeah, Burnham Lake. So City Hall, you can kita parang may tower dyan. Yan yung sa may, I think, park in front of City Hall. So on the upper right is around Session Road, Lakandula, Harrison. Okay? So mapapansin nyo, nai-infect niya. But if you look at this particular area here, this portion initially does not have an infected person, which means hindi siya makagalaw rin. Okay? So there's no path going out, even though if there's a random, then even if you try to look at the simulation, it goes on, and the chart display will be have this one. As you can see, expectedly in in a in the ODE model, this should approach what the maximum. So it will have totally infected, okay, and totally uh, susceptible going to zero. Okay, because of this integerization, obviously, and some constraints in the model, you will get that one. Okay, so yeah, and you can since you have a map, then I can locate those agents. Either if I try to simulate it, I can look at its position, and if I look at the road map, then these are the roads labeled in the shapefile. Okay, and I can identify them. This is the location, the grid, and uh, you can also look at it in terms of buildings, so where they are located, or in terms of the description of the people, if it's infected or not, and its corresponding speed, and its heading, meaning the direction, yung target. Okay, so even if you let this run all throughout, obviously, this one is this will stay green. Okay, so here you now have a concept where what you can do is, if I were to look at a simulation of a particular area, then what I can do is what do you call this? What I can do is isolate them, meaning that's why the lockdowns is a way of showing that you block the road, and in terms of the simulation, you disconnect the roadmap. Okay, so the polygon that should be continuous all throughout becomes disconnected. Okay, so that's one which you impose on the conditions of the shapefile, or you may limit the what do you call this, the target or the attributes of a particular agent. Okay, so that it will not go to that particular area. Okay, so uh, again, this is a way of showing some decision makers to see what will really happen if I consider this setup again. I have to limit the number of infected, and if I simulate, and you can see there's only limited movements of those humans. Okay, and at some point, some of those regions or buildings will not get infected. Okay, because initially you don't have. It's possible that you don't have an access to that building. Okay, and initially there's no one infected there, which is a way of again illustrating what will happen if you let all the borders open. So you can look at it in a larger scale, and each building here can be a particular area or barangay or town, okay, or a city. And if you disconnect them via those roads, meaning you have a lockdown, then you can simply have clustering only of those infected people. Okay, so again, This is only a way of visualizing uh, the dynamics of your disease model and show you. And what you can do also is incorporate again labels here. Okay, so if I were to look at the map again, so this region on the upper right corner will not get infected. Okay, so kung titingnan nyo, hindi na ma-infect yung mga yan. Okay, and you can see how those roads will be or those agents are labeled, meaning are they infected or not. And you can particularly what you call this mark. Okay, kunwari ang isang person like 28, so I mark it. Okay, so I can also kill it in such a way that I can just remove it from the population. Okay, or you can also mark a particular person here so that when you want to track it down, it will be labeled as a different color. Okay, so again, let's say I'll mark this one, but I think this should be marked differently. Or what happens is like if let me go back and start this one. Uh, let's say I have a map. I can mark a particular person here. Okay, so you can look at this one and monitor or change its attributes. Okay, so you can name it as a particular person and then monitor its movement. Okay, meaning I will label it as a particular color. Okay, so pwede mo ring tignan kung infected siya and then palitan mo, gawin mo siyang what you call this, infected. Okay, and then continue with the simulations. So I think this can be a tool really to at least visualize, help visualize what's happening, and at the same time to monitor. Okay, so you can be proactive in such a way that if you have some people moving around, that's why maybe putting a tag on a particular person, if it's possible, can trace if it moves to that point and goes to a particular section where no one is infected, then it's a possible way to infect everybody. Okay, so ito, gumagalaw sila. There's some people moving around. And again, kanina itong upper right was not infected, but since you have one infected person on that building, initially at random, then it was able to infect almost all the people in that building. Okay? So depende ngayon kung ano yung initial locations. So to be more realistic, then you can label them and then pinpoint a particular part where they are located. Okay, so I think that ends, and maybe just to give you a 3D, this is one picture that they are able to incorporate. I think you can now have a way of visualizing it. Okay, and it's like simply a movement of one person to another, okay, wherein you have a particular building being taken into account. Okay. Okay. So I think that ends my talk, and you can do a lot from this agent. So that's it for today. Thank you. And thank you for listening.
All right. Thank you, Sir Joel, for that very informative and interesting way to really visualize how the COVID-19 or any infection is being spread. And probably we can entertain a question or two. Um, Do you have any questions? Okay.
Ayaw nyo mag...
Ayaw nila ata, sir.
Baka ako gusto nyo magtanong.
Okay. While you think of a question or two, maybe we can, may I request you to please start your videos for a couple of minutes so that we can take a picture as proof that we have view gallery. Okay, let me try. Okay. May I request everyone to please switch your videos on? Okay. Kaya mag-ingat. Mag-ingat lahat kasi nakakatakot, mabilis mag-spread yung disease. Okay. All right. Ready? Some of you, okay. Defective po camera ko. Okay, sir. I think your name is here naman. All right. Okay. I'll count. All right. 1, 2, smile. Hang on. Okay. Another one. 1, 2. All right. One more set. Okay. We have 1, 2. Okay. One more. Sana lang. Ay, saglit. O, sige. Si ate nag... Okay. Okay ka na, te. All right. 1, 1, 2. Ay, ba't ayaw na? 1, 2. Okay. Thank you so much. Okay, we have the plenary speaker, our last talk for today, which is on another link. Okay, the evaluation for Professor Adawe is already in the link. So please have time during the break to evaluate Dr. Adawe. And we'll see you in the plenary talk of Dr. Isabel Adawe also. All right. So again, thank you so much, guys, for participating in Track D. And I hope you can share what our lecturers have shared in your respective institutions, and and you can apply it in your work or in your lives. Okay. If you don't have any more questions, we will be in the other Zoom for the plenary talk. Okay. So thank you again, and stay safe, everyone. Thank you.
Bye-bye. Thank you,
Bye-bye.
everyone.
Bye, sir.
Thank you po.
Thank you, Dan. Okay. Last na.